All right, so if you have your microphone on, if you could turn it off, that would be great. And again, if you have a question, feel free to unmute or to type it in the chat, and I will do my best to answer that. Well, let's start talking about quantum theory and atomic structure. You might be intimidated just from the first slide. You hear the word quantum, and you might have heard of quantum mechanics. Now, that's a class I took in my third year of my chemistry degree, of my bachelor's degree, and that required second year calculus just to get into the class. And so we're not going to be looking at quantum mechanics at that kind of level, but we will talk about it at a lower level, at a level that we can understand without calculus. But before we get into that, let's talk about light a little bit. And light, visible light, is a type of what we call electromagnetic radiation. So electromagnetic radiation is not only things like visible light, it's also infrared light, ultraviolet light, and we'll talk about the other types of electromagnetic radiation in a bit. But it says here that the wave properties of electromagnetic radiation are described by three variables. We can describe it by the frequency, which is the number of cycles of the wave per second, okay? The wavelength, which is the distance between successive points on a wave, and I'll show you a picture of that because a picture is worth 1,000 words. And then the speed, which is the distance the wave moves per unit time, and we usually measure that in meters per second. Also, the amplitude of the wave, which is the height of a wave crest or the depth of a trough. And again, I have that on a picture coming up. And you need to be aware of the speed of light. Now, I usually give my students the speed of light on a handout that will be provided. But you should have this, I think, at your disposal. And the speed of light is equal to the frequency of the light multiplied by the wavelength of the light. And if you think about it, the units of frequency are cycles per second. So that would be cycles per second. So 1 over a second, or seconds to the minus 1. And if you think about wavelength, we could report that in meters, right? It's a distance. So if you take frequency in 1 over seconds, or seconds to the minus 1 times meters, what would that give you? Meters per second. So that seems to make sense. And the speed of light in a vacuum is 3.00 times 10 to the 8th meters per second. So it's pretty fast, okay? And any light is going to travel at that speed in a vacuum. It doesn't matter if it's ultraviolet light or infrared light or visible light. And I think it's a good idea to have this value in your brain, okay? It's just something that we use so often in this chapter, so it's probably a good idea to memorize that. All right, here we go. So here's the relationship of frequency and wavelength. So you can see here that we have three different waves, A, B, and C. It says here that the wavelength, again, is the distance per cycle. And you can see, and the way I described wavelength was what? I said it was the distance between successive points on a wave. So if you look at this wave here, if you've ever studied physics before, you probably know that the very top of a wave like this, we call that a crest, right? And the very bottom of a wave, we call that a trough. So if we measure from a crest to a crest, that gives us a wavelength. And you can see here that the wavelength of A is longer than the distance between two crests in B, which is the wavelength of B. And then the wavelength of B is longer than the wavelength of C. Now, if you think about this distance, right? If you think about this distance starting here, if all of these start at t is equal to 0, and let's say that this is 1 second, right? If we say that this is t is equal to 1 second, and this is just a number I chose arbitrarily. It could have been t is equal to 20 seconds. I don't care. It doesn't matter. What I want you to understand is that the frequency is the number of cycles per second, and I want you to understand the relationship between wavelength and frequency. And you can see that the longer wavelength we have a shorter frequency. Okay, so the longer wavelength, we have a shorter frequency. And when we have a shorter wavelength, we have a higher frequency, right? We have more waves occurring in that period of time. And if you think about it, that makes sense because I told you earlier that the speed of light is equal to frequency times wavelength. So if I rearrange this and I solve for frequency, I can see that frequency is equal to the speed of light divided by wavelength. And then you can clearly see that frequency and wavelength are inversely proportional. Okay, so again, we have long wavelength, and I know I'm spending a lot of time on this, but I want to make sure that you understand. If we go from long wavelength to short wavelength, okay, we go from high frequency, or I should say low frequency, to higher frequency, okay, like that. All right, just things to think about before we move on. Let's talk about the amplitude of a wave for a second, of our light wave. And you can see that the amplitude, okay, is the distance between this center line here, or this baseline, okay, and the top of a crest. Oops, the top of a crest like this. And so with respect to electromagnetic radiation, now if you think about something like visible light, why is a light brighter? If you could have a dim red light, let's say, or a bright red light, well, the brightness is related to the amplitude of the wave, okay? So brightness is related to amplitude. Somebody has their microphone on. If you could turn it off, that would be really great. All right. Well, with all those things in mind, let's move on and talk about the electromagnetic spectrum. Every chemistry student or physics student should have some working knowledge of the electromagnetic spectrum. I'm just going to throw this equation up here, which is the speed of light, and this is equal to frequency times wavelength. I'll just point out that this is any light. It doesn't necessarily have to be visible light or any type of electromagnetic radiation. If you look at this scale here, you can see that down here at the bottom, if we look at wavelength, so I'm talking about wavelength down here, we have long wavelength, okay? That means we're going to have low frequency, right? And frequency is down here, right? And at this far left down here, we're going to have short wavelength, and they're going to have high frequency, okay? Now, in terms of the electromagnetic spectrum, what we can see with the naked eye is lies in a range of wavelengths. Okay, so I'm talking about wavelengths right now, somewhere between 400 and 750 nanometers. Those are the wavelengths that we can see with the naked eye. Now, this part of the electromagnetic spectrum that's highlighted here, this is actually exaggerated. This distance here between these 2 points, that's actually exaggerated. What we can see is a very, very thin slice of the entire electromagnetic spectrum. Now, you've probably all heard of ultraviolet light, okay? And ultraviolet light has a shorter wavelength, right? Ultraviolet light is found right here. We cannot see it with the naked eye. It has a shorter wavelength, and it has a higher frequency. Beyond that, we have X-rays, which have an even shorter wavelength and even higher frequency. And then beyond that, we have the gamma ray, okay? And if you've ever heard of the Incredible Hulk, I think he's the one maybe who was exposed to gamma rays, which I wouldn't recommend because that would, generally speaking, be a deleterious, cause deleterious effects to the human body. But I think for the Hulk, who doesn't seem like a genius for exposing himself to gamma rays. But anyhow, I digress. Where the heck was I? So if we go the other direction from visible light, if we go to the next longer wavelength, we have infrared. Sometimes we just call that IR. You've probably all heard of infrared goggles or infrared, whatever they call them, that maybe the police have or something for night vision, or night vision goggles. Sorry, that's what I was looking for. Then beyond that, we have microwaves. Something interesting about microwaves is that they are longer than infrared and longer than visible. And there's a specific frequency of microwaves that cause water molecules to absorb energy, and that's why you can use a microwave to heat up your food, because your food, has water in it. And then beyond that, we go to radio waves. Radio waves are really big, they can be up to the size of a building and even bigger. So they have long wavelengths, but they have low frequencies, okay? There's something else that you're probably thinking of, and I'm sure many of you are thinking about this, while I'm talking about this, is, hey, isn't any of this related to energy, right? Because radio waves are passing through all of us right now. Every single one of us that's hearing my voice, we all have radio waves that are going through our body right now, from cell phones and communication towers, what have you. And I'm not feeling anything. I'm not like, oh man, the radio waves are getting me today. No, we feel nothing, okay? Whereas, like I told you, if you were exposed to gamma rays, that's not a good thing. Even if you've had an X-ray recently, right? Prolonged exposure to X-rays is not a good thing either. That's why they put, you know, if you go to the dentist and they take an X-ray of your mouth, that's why they put a lead vest over you, is to prevent the rest of you from getting exposed to X-rays. Why does the X-ray technician hide behind, you know, a wall? Well, she or he doesn't want to be exposed to X-rays either. And if you're wondering, like, hey, Mr. Dion, when are you going to get to the connection between, you know, of the electromagnetic spectrum and energy? I'll do that in a little bit. Okay, we'll look at that in a few minutes. But before we get into that, let's go to this slide here, which talks about interconverting wavelength and frequency. So let's try a practice problem here. This is the typical kind of problem you would be asked on your next midterm. It says a dental hygienist uses X-rays, which have a wavelength of 0.50 angstrom. If you don't know what an angstrom is, it's a really exotic units of distance, of length, sorry. And it's basically, an angstrom is nothing more than 10 to the negative 10 meters. If you've never heard of an angstrom, don't stress about it. Anyhow, so if you have the wavelength of half an angstrom in your X-ray to take a series of dental radiographs while the patient listens to a radio station that has a wavelength of 325 centimeters, that's a long wavelength, right? That's 3.25, you know, meters. So that's like, you know, more than 3 yards. It's about 3.5 yards long. And the person looks out the window. Wow, this person's really got some wavelengths in their life. They're looking at the blue sky. Blue light has a wavelength of 473 nanometers. What is the frequency in cycles per second of the electromagnetic radiation from each source? Assume that the radiation travels at the speed of light. All right, well, I mean, they're kind of asking the same thing every time here. You guys know this formula. I already told you that C is equal to frequency times wavelength. And they're asking us, where's my pen? There it is. What's the question asking us? They're asking us, come on, Mr. Dion, what is the frequency in cycles per second? So if we want to solve for frequency, we can say that frequency is equal to C divided by lambda. So that means that all we have to do for each one of these is we just have to divide the speed of light by the wavelength. Now, what are we going to have to do, though? Because our speed of light is given in meters per second, we're going to have to convert all three of these into meters, and we have all of the conversion factors here. Let's just do, the X-rays and the radio signal. We'll just do those right now. So, and then I'll let you try the other one at home. So again, we're going to use our formula, which is speed of light is equal to frequency times wavelength. We're going to solve for frequency is equal to speed of light divided by wavelength. We have our 0.50 angstroms. Maybe I could solve that first. We have 0.50 angstroms, and I know that in 1 angstrom, I have 10 to the negative 10 meters. So let me go back here. I know that in 1 angstrom, I have 1 times 10 to the negative 10 meters. And so that's going to be equal to 0.50 times 10 to the negative 10 meters. I'm just doing it in my head, actually. Just an easier way to solve it. Anyhow, so when I plug that into my equation, I get 3.00 times 10 to the 8 meters per second, and I divide that by 0.50 times 10 to the negative 10 meters. Meters and meters cancel out like that, and I end up with this number, which is only has 2 sig figs, 6.0 times 10 to the 18 seconds to the minus 1. Does anybody know, and I know somebody out there knows, what's the other unit that I can use for reciprocal seconds, or seconds to the minus 1? There's another sassier way I can report that. I knew it. I knew that you guys would know. Yes, the answer is hertz. Very good. So a second to the minus 1, or what I call a reciprocal second, that's equal to a hertz. So hertz is nothing more than cycles per second. So we could also say 6.0 times 10 to the 18 hertz. There we go. Perfect. Could you do the next one? Of course you could, right? To convert 325 centimeters into meters, you know that there's 100 centimeters in 1 meter. So this equals 3.25 meters. We use the same formula. Frequency is equal to C over lambda. We plug in 3.00 times 10 to the 8 meters per second. We divide by 3.25 meters. Looky, looky. Meters and meters cancel out. And we end up with, I've already done this one, I think, here. Look at my scratch paper. I get 9.29. Does that sound right? 9.29 times 10 to the 7 reciprocal seconds. Did anybody else get that? I did it, but my handwriting is so messy I can barely read it. All right.
It's 9.23, but close
Is
enough.
it 9.23? Yeah, I told you. I knew I couldn't read my handwriting. Let me double check. I'm sure you're right. Times 10 to the 8 divided by 3.25. You know what? You're absolutely right. It's 9.23. You know what my excuse is? I'm not sure who unmuted their mic, but my excuse is that I did this upstairs at my kitchen table, and I was too lazy to go grab a pencil, and all I had was my kid's colored pencil, so I couldn't erase it, my answer. So anyhow, I guess I could have just looked at the next slide, couldn't I? Oh, jeepers. All right, and then the answer for the blue sky problem is here too. All right, so let's examine some distinctions between the waves of energy and the particles of matter. So when we think about our electromagnetic radiation, our light is being a wave, right? Light waves, okay? And then we think about matter as being particles. And where we're going with this, I'm trying to give you the best introduction to, what the heck I'm trying to explain here, which is we're going to get into explaining some of the particle behavior of energy and some of the wave behavior of matter, which is not intuitive, okay? That is why quantum mechanics is a difficult subject. It's not intuitive, okay? But we're going to try to look at some of the distinctions first between waves of energy and particles of matter. So if we think about waves and particles, well, the first thing we're going to look at is refraction. Okay, so it says here that when a wave changes its speed and therefore its direction as it passes through a phase boundary into a different medium, we call that refraction. And so you need to know what refraction is. And everybody that's hearing my voice has seen refraction before. I wouldn't I'm holding my Apple Pencil right now. I wouldn't stick that in water because it would ruin it. But if you've ever looked at a spoon in a glass or a pencil in water or something, and you have part of it sticking in the air, it looks like it's bent. And the reason why is because when the light travels from the air into the water, you have a different angle of refraction. And it causes the light to bend its path, and so you actually see the pencil bent at a different angle, okay? And that is based on refraction. So we have, again, and I'm just repeating myself here, we have our light wave. It's going from air to water. The light wave is going to bend, and it bends immediately. Okay, it changes its path immediately, and we call that the refraction of light. Okay, what about a particle? Well, you're probably thinking, well, come on, if I throw a pebble into water, it's going to change its trajectory, right? But it's not refraction, right? Because it changes its speed gradually. It changes its angle gradually, right? Speed and angle gradually, right? So it's not refraction. So the wave undergoes refraction. The particle does not undergo refraction. All right, so that's refraction, the bending of a wave or the changing of its direction when it passes from one medium to another. All right, and if you're like, well, is this what happens when you take a light and you shine it through a prism? Yes, it does get bent inside the prism. All right. And here's a picture of that, right? It kind of looks like a Pink Floyd album cover, right? Dispersion is what happens when white light is separated or it gets dispersed into its component colors when it passes through a prism. So a prism, and if you're like, well, isn't this refraction? No, the prism is doing the refracting, right? So it says here that the prism is a refracting object, but what's actually happening to white light? So white light is made up of all wavelengths of light. When it's coming out the other side and you get this rainbow, you get the Roy G. Biv, right? You guys know about Roy G. Biv? Roy G. Biv. Does anybody know about Roy G. Biv? Has anybody heard of that before? Yes, okay. A couple people have. If you're like, who is Roy G. Biv? Is he some kind of new singer or something? No. Roy G. Biv stands for red, orange, yellow, green, blue, indigo, violet. And my father-in-law, I told him, I said, have you ever heard of Roy G. Biv? He's like, of course I have. He said, in Kansas City, there was a guy who had a painting company, okay? Who had a painting company, and on his company truck, so this is the truck that he had. He's like, on the company truck, the guy actually had written on the name, he said his name was Roy G. Biv. It wasn't his name. His name was like Ken or something. And they were like, hey, it's Roy G. Biv Painting Company. Anyhow, cheeky guy. All right. Anyhow, there we go. Okay, moving on. Anyhow, so we've got dispersion down, and we've got refraction down, and we've got Roy G. Biv down. We're cooking with gas here, people. Let's move on. Now, we're going to look at what's called diffraction. So we've got refraction. Okay, we covered refraction, we covered dispersion, and now we're going to talk about diffraction. So it's kind of like mixing those two words together. So it says here that when a wave strikes the edge of an object, okay, it bends around it in a phenomenon called diffraction. So if you have some waves, you have a bunch of waves here in the diagram C, and they're all heading towards this slit that's shown right here. It says the wave bends around both edges of the small opening, which I call the slit, forming semicircular waves, and that's called refraction, right? It's bending around the edge of an object. Now, if we take particles, okay, if we take some particles and we throw them at a slit, some are going to hit the edges, but some are going to pass through, and they are not going to be diffracted, okay? So a wave is going to undergo refraction and diffraction, but particles will not, right? Imagine, this is the way I described it to my students last semester. I remember it very well. I said, imagine you took your hand and you threw a handful of sand at a wall, right? Just throw it, right? Well, some of them are going to hit and bounce back, but some of them, the ones that make it through the slit, are just going to pass straight through, okay? So again, the wave undergoes diffraction, refraction, dispersion, but the particle does not. All right, so some interesting definitions to get us, kind of cooking here. Now it says the formation of a diffraction pattern. Okay, so it says here that in contrast, particles passing through adjacent openings continue in straight paths. Now that was what I mentioned on the last slide. But if you look at what's happening here, okay, it says we're taking light waves. So if we take lights adjacent, and we have two slits here. Maybe you can't see where I'm pointing. Let me get my highlighter, okay? I have a slit. Oh, that's not a highlighter, is it? So I have a slit here and a slit here, okay? And I shine a light. Now, those slits have to be really narrow. They have to be about the same width, as the wavelength themselves. But what's going to happen is that it says here the light waves passing through the two slits emerge as circular waves, and they have constructive and destructive interference as a result of a diffraction pattern. So the light waves form a diffraction pattern. So where the light waves overlap with each other, we call that constructive interference. So if we have two light waves overlapping, they produce a spot that's even brighter. So that's all these here. It's even brighter in here. And when they cancel each other out, so if they're completely out of phase with each other, like this, then they cancel and you just get a flat line. And that's what causes all these areas of darkness here from our light waves. All right, and then it says here, constructive and destructive interference occur as water waves pass through two adjacent slits, okay? There we go. Well, with that in mind, let's move on from here and let's talk about energy and frequency for a little bit. So going back, I'm going to switch gears here a little bit. As everything in general chemistry, since it's general chemistry, right? You think about it, there's nobody who does research in just general chemistry. Everybody has an area of research. And so in general chemistry, that's why we tend to switch gears a lot, right? We jump around, we have to access a lot of different parts of chemistry to make part of a really big story. And so now we're going to go back to that electromagnetic spectrum for a second. Now, if you have a solid object, okay, and you heat it up hot enough, you might notice that it emits visible light. And we call that black body radiation. Now, if you look into the history of blackbody radiation, if you're like, what the heck is blackbody radiation? This is all they mean by blackbody radiation, right? If you take coal, you heat it up, you don't have a fire. If you've ever seen coal, coal's in a fire. Well, why are they giving off light, right? Just because they're heated, okay? It's not a fire, they're just giving off light. If you take electric heating element, that's even hotter, and it gives off an even brighter light. And if you have something that's even hotter, it can give off like a white light. And what I'm going to get at here is summarized here, is that people trying to explain these wavelengths of light and tried to connect it with the energy given off by the hot object. And the problem is that they couldn't use classical mechanics to explain the relationship between the energy given off by the hot object and the wavelength of radiation emitted. Now let me back up here and explain this slide right here, okay? So it says here that a solid object emits visible light when it's heated up, okay? So again, so that's called blackbody radiation. I just explained what blackbody radiation is. It sounds complicated, but it's just, again, heating something up, it emits light. Okay, cool. Now let's go back to the color of that light. It says here that the color and the intensity of the light given off by the black body changes as the temperature changes, right? That's what I just showed you on the next slide, okay? I'll get ahead a little bit of myself. The color, right? We saw this in the Roy G. Biv, right? In the electromagnetic spectrum, that the color of light is related to its wavelength and frequency, while temperature is related to energy. So what we got two different things, right? We're trying to connect energy and we're trying to connect wavelength and frequency, okay? And so the explanation is that energy is got to be related to frequency and wavelength. And so Planck came up with this equation. So a person named Max Planck came up with this equation, which says energy, which is E, is equal to H, which is Planck's constant. And I'll tell you what Planck's constant is right now, just so you are aware that it's just a constant number. It's 6.626 times 10 to the negative 34 joules seconds, okay? That's a constant that I would give you on your midterms, on your final, whatever. You don't have to memorize that number. You probably will if you do enough practice problems. But energy is going to be equal to Planck's constant times what? What's this symbol here, right? I don't know if I mentioned it earlier, but this is the Greek letter nu, and of course that equals frequency. Now, what I was getting ahead, I kind of got ahead of myself here, but I was dying to show you blackbody radiation because I remember hearing about blackbody radiation for the first time, and I was like, what is that, okay? So the thing is when they tried to make the connection between the energy of the heat given off and the wavelength of the light, there was it didn't connect, right? There was many theories that were postulated, but in going into the history of it, it's not a history class, but basically one theory worked for long wavelengths of light and the other one worked for short wavelengths of light, but nothing worked for all wavelengths of light. They couldn't find that connection between energy and the wavelength of the light. And so when Max Planck came along, it says, even in our textbook, it says basically through an act of desperation, he came up with an equation that works, okay, that explains the wavelengths of light and the connection to the energy that's given off in blackbody radiation. And what he postulated is this. He said that any object, including atoms, can emit or absorb only certain quantities of energy. Wow, that's really different than what we're used to, right, in classical mechanics. And if you're like, what's classical mechanics? Okay, all I mean is in our everyday of life, we could think about any quantity of energy, but what he's saying is that energy is in fact quantized. And if you're like, what does quantized mean? I'll get to that too. It says here that energy is quantized. That means it occurs in fixed quantities only rather than being continuous, okay? So the whole idea behind energy being quantized, this is where quantum mechanics comes in. Quantum mechanics. The idea of energy being continuous, that's classical mechanics. Okay? If you've ever studied physics before, classical mechanics. Each fixed quantity of energy is called a quantum. Now it says here that an atom changes its energy state by emitting or absorbing one or more quanta of energy. And so what Planck discovered is that the energy was related to Planck's constant times frequency. So energy and frequency were related, okay? But he also discovered that it was only that this equation only worked when you multiplied it by n, where n is a whole number. So it always had to be some multiple of a whole number. That means it couldn't be 1.1 or 1.5. It had to be n had to be a whole number. What's a whole number, right? 1, 2, 3, 4, 5, 6, and so on. Now the next slide I think has the photoelectric effect. Let me back up and just talk about quantum and quantization just for a second. It's very rare for me to turn my presentation off, but I'm just going to show you my face here for a second. And I'm going to try talking with my hands to my students, okay? So if you're hearing my voice out there, don't be scared of the word quantum, okay? It's something that we use in everyday life. For example, if I was to count students, right, I would say, okay, I have 100 students. I would never say I have, 100.5 students, right? We don't talk that way. So people are something that's quantized. Now, if you're thinking like, hey, Mr. Dion, isn't that the same example you used for exact numbers? Is it the same thing? No, it's not the exact same thing. Another example would be, and I'm not probably the best person to explain this, but would be the musical notes on the scale. So if you have do, re, mi, fa, sol, la, ti, do, right? There are frequencies, right? There are notes that are in between technically, but we don't use them. We say the scale is quantized. In fact, one of my students explained this to me one time. They said, well, if you take a person and have them sing a song in a recording studio and you select the wave file of the person singing, what you can do is actually just click a button in a computer in a recording program now, and it will quantize the notes that the person sang so that they will all match up perfectly with the notes on the scale. So if the person was sharp, if they were above the note, or if they were flat below the note, it will quantize it. So what does that mean, right? All I'm saying is that music is made up of specific notes. There are notes in between, but we call those being flat or sharp or somebody singing off key. Okay, another example would be this. I'm giving you a lot of examples, okay? Say I had my Apple Pencil. Maybe it's not the best example. I'm trying to think. If I had, let's say you had a tire, on an axis, and you were rotating a tire. If I said, I want you to rotate that tire at 60 miles an hour, you'd say, okay, that can be done. I want you to rotate that tire at 60.1 miles per hour. You're like, okay, sure, I guess it can be done, right? Just speed it up a little bit. If I said to you, is it possible to spin that tire at 60.125798, whatever miles per hour? Is that possible? It'd be like, yes, it's possible. You could spin a tire at any speed. Well, what quantization means is that it can only spin at certain speeds. And you're like, well, how could that happen? That's why quantum mechanics is not intuitive, right? Classical mechanics tells you that, well, energy is equal to h times nu. I could have any, type of energy I want, or any value of energy I want. Go back to sharing my screen here. Okay. But what Planck discovered is that the connection between the wavelength and the energy is that it was, am I still recording? Good. Is that it's quantized, right? It can only be specific values, okay? So it has to be specific quanta of energy. That means it can't be any energy. And if you're like, I still don't understand you 100%, Mr. Dion, well, don't stress about it too much because we'll talk about it even more as we move along, all right? Let's switch gears again, okay, and talk about the photoelectric effect. I'm going to make this really brief because the book goes into quite a bit of detail, but a lot of people think that Albert Einstein won the Nobel Prize for this equation that you see on all manner of posters and t-shirts, which is E is equal to mc squared, and he did develop that equation, which shows the relationship between energy and mass, also counterintuitive, but what he won the Nobel Prize for was what's called the photoelectric effect. Okay, and what the photoelectric effect is nothing more than this. So what he did is he took an evacuated tube and he took a metal plate, okay? So he had a metal plate and he had that connected to a wire with some kind of current measuring device, and he had an electrode in there. So he has a positive electrode here hooked up. And what's going to happen is if we could knock electrons off of this metal, right? There's electrons in the metal. If we could knock electrons off, right? We need to have moving electrons in order to conduct electricity, and we could measure that current. And if you're like, well, how am I going to knock electrons off? You told me that an electron has a mass. We discussed that earlier on in the class, right? Electrons are really light. Well, what he did is all he did was he shined some light on it. So it says incoming light strikes the metal surface, and he was able to measure a current. What? Yeah, so think about it. We think about electrons as being a particle that have a mass up until now, right? You think, okay, yeah, electrons have mass. Yeah, you told me what they weigh earlier on in the class when we discussed protons and neutrons. I said, well, an electron weighs about what? 1,820 times less than a proton or a neutron. They're very light. But what he's doing here is he's taking a wave, right? He's taking a wave of light. He's shining it at something, and he's getting a particle to knock off. That's like me saying, hey, could you help me push this car, across this parking lot? Hold on, Mr. Dion, let me go grab my flashlight, and I'll just, shine it on your car there, and that'll move it. Like, whoa, that's really intense, okay? So this is what he won the Nobel Prize for, okay? And the explanation for this, okay, how he explained this is that light is actually made up of tiny little bundles of energy called photons. And so he said, well, not only does light have a wave nature, it also has a particle nature. Now that might just be like, what? How could that be? How could light also be a particle? Well, I didn't say that light was a particle. I said that light has the nature of a particle. Well, with that in mind, that's a lot of me talking, and I know it's never good to talk for too long without trying a practice problem. So let's, get down to brass tacks here and solve a problem as a group. It says here we're going to interconvert wavelength, energy, and frequency. It says a student uses a microwave oven to heat up a nice, delicious meal. The wavelength of the radiation is 1.20 centimeters. What is the energy of one photon of this microwave radiation? So the energy, remember I told you that a photon is like a little packet of energy. It says here we know the wavelength in centimeters, and so we convert from meters to find the frequency using the speed of light. Then we find the energy of one photon. So I showed you this equation earlier on in class today. The energy is equal to Planck's constant times frequency. I also showed you this equation that the speed of light is equal to frequency times wavelength. Well, I can solve for my nu, my frequency, which is equal to the speed of light divided by wavelength, and all I'm going to do is take this and plug it in here, and I get this equation, which you already, oops, I didn't mean to do all that. Good grief. On my slides. There we go. And I end up with this equation right here, which is E is equal to HC over lambda, like that. Okay, I'm going to erase some of this spinach. And again, I always recommend to my students that you should try all of these problems before coming to class. I highly recommend doing that. And so let's give this one the old college try. Now that I've got a little bit more space. Come on. There we go. So I'm going to say that E is equal to Planck's constant, which I told you earlier on today was 6.626 times 10 to the negative 34 joules times seconds, multiplied by the speed of light, 3.00 times 10 to the 8 meters per second, divided by my wavelength. Could you convert 1.20 centimeters into meters? If you can't, I can help you out. In 1.2 centimeters, I know that in 1 meter, there's 100 centimeters. And so you can see that centimeters cancel out, and I end up with 0.0120 meters. Now all I have to do is plug that into my equation up here, 0.0120 meters. I should have 3 sig figs in my final answer. And so when I punch all of this spinach into my calculator, you can see that meters cancel out, seconds cancel out. What unit am I left over with? Joules. And joules is a unit of energy. And so for an answer, I got that E is equal to 1.66 times 10 to the negative 23 joules, like that. So there's my energy. Okay, so that's a really small amount of energy. You're like, that's not much energy. How can I heat up a meal with that little amount of energy? Remember that this is one photon. Now, this is just an analogy that was developed by one of my colleagues, but he said, like, one photon is to like a burst of light as, you know, an atom is to an element, right? So it takes a lot of photons to make, you know, a burst of light, okay? Anyhow, and we'll look at some examples later on where we calculate the number of photons that it would take to heat up a block of ice or something like that, or melt a block of ice. It's one of the classic bonus questions in Chemistry 1401. All right, this, I don't do a lot of these kind of fill in the blank questions, but I just thought we'd kind of do this to kind of slow down just for a second, clear our minds, and make sure that we're all on the same page about frequency, photons, energy, wavelength. And I'm sure that most of you have this down pat. You're not stressed about it. But just to be sure that we're all on the same page, it says here, the blank, and it's either frequency or velocity of a photon of light, is directly or inversely proportional to its energy in blank to its wavelength. Well, when we're talking about a photon of light, we're talking about the frequency of a photon of light, right? From our equations, right? We said that E is equal to hc over lambda, or you could write it E is equal to h times mu. So the frequency, so we'll put here the frequency of a photon of light is blank proportional to its energy. Would that be directly or inversely? I don't know what, it should say directly or indirectly, but who could help me out? Yeah, thanks, Violet. It's directly proportional. So directly proportional to its energy, and it's going to be what to its wavelength? Well, if we have this formula, C is equal to mu times the wavelength, we can see that wavelength, and I did this earlier, but I'm just repeating myself like an old man. 43, I've earned the right to repeat myself. Tell my wife that. Thank you, Matthew. Thank you, Gabriella. Yeah, you're both absolutely right. The answer is that they're inversely proportional. So we'll put that in here, inversely. All right, give me a thumbs up if you follow me thus far. Just kind of getting started here. All right, Jordan says thumb. Matthew says thumb. All right, good enough. All right, well, let's keep cooking with gas here. And it's kind of a fun lecture talking about, you know, if you're wondering, like, where are we going with all this? What's your point? So just talking about light. I thought this was a chemistry class, you know? You know, sometimes it's a good idea to ask yourself, like, why am I learning this? You know, why is this important? Well, you have to actually do all this kind of historical stuff just to understand the structure of the atom. And I'll take it one step further, is that really for the next few minutes, all we're going to talk about is the structure of one atom, and that's the hydrogen atom, really. Okay? In fact, we spend a lot of time in this chapter just talking about hydrogen. And if you're like, well, Mr. Dion, there's like over 100 elements in the periodic table. Do we have to talk about every single one of them in this kind of detail? The answer is no. Hydrogen is the simplest element, and actually studying the hydrogen atom actually developed into our understanding or modern atomic theory, which we use to explain the structure of all atoms. So let's get going here. And this is a lot, it shows the line spectrum of hydrogen. If you're just like, Mr. Dion, this looks like some boring lines on a black line to me. Well, if you've ever been in a chemistry lab before, or maybe in a chemistry classroom or something, you might have seen sometimes labs that will have posters of this up on the wall, and they'll be like, check these out, aren't these cool? What these are is nothing more than this. If you take pure hydrogen gas and you put it inside an evacuated bulb, so what's inside here? This is hydrogen. Okay, it's just H2 gas, and then you pass a current through it. What you get is this kind of pinkish light. Okay, you get this kind of pink light, and you're like, okay, pink light, cool. So if you see a pink light, you might have the knee-jerk reaction to say, well, if I look at the whole visible electromagnetic spectrum, the wavelength of that light must be somewhere maybe around here. Is that pink? Or maybe around here that looks kind of pinky to me, or maybe it's here, you know. You say maybe it's one of those, you know, it's in the pinky region of the visible spectrum. Well, in fact, if you take that light from the hydrogen gas discharge tube and you shine it through a prism and you look at the diffraction pattern, actually what you end up with is nothing more than 4 lines. You just get 4 measly lines. And if you're like, well, hold on, Mr. Dion, I thought when you took a prism and you shone light through it that you got the whole Roy G. Biv. What about that? No. That was when we took white light. Okay? White light possesses all wavelengths of light. I'm talking just about hydrogen. Okay? The light bulbs in your house, trust me, they're not filled with hydrogen. Okay? So for that hydrogen atom, you do that and you just see these 4 wavelengths. So you have a violet one here, you get an indigo, you get a blue, and you get a red. Kind of cool. You can do this with any element. Look at this. I'll just skip way ahead, you know, because I'm probably taking too much time today, but I'm just enjoying kind of walking through this with my students. If you look at neon, it's maybe not abundantly clear by looking at a slide, but I can tell you that the lines here that are kind of in the yellow region and the red, they're really intense. And that's why neon has that kind of bright, you know, neon colors, right? It's because those are the brightest lines in the spectrum. And if you're wondering, well, could I use this? If I just took a gas discharge tube and I looked at the wavelengths, if you told me, Mr. Dion, that every element, you know, gives a unique spectrum, line spectrum, could I use that to identify an element? The answer is absolutely yes, you could. Absolutely. In fact, I've gotten students to do that in the lab before. I'll give them a gas discharge tube and I'll say, there's some kind of gas in there, you figure it out. Okay, and what they would do is they'd look at it through a refractometer, look at the wavelengths of light, and then they'd go to a chart, and then they'd be able to identify the element. Okay, it's not rocket science. I mean, it's not simple either, but it's a way to be able to identify an atom. Anyhow, before we move on to the next slide, you might be asking yourself, why? Why, Mr. Dion? Why is it that when I take hydrogen, why can I see these 4 lines? Like, why the heck is this happening? You know, why is it that when I take neon and shine light through it, or sorry, pass a current through it, why do I get these lines? Okay, well, the answer or the solution to this, okay, was actually determined by a scientist named Johannes Rydberg, and he developed this equation here to explain the spectral lines that he saw for atomic hydrogen. Okay, so again, you take your hydrogen, gas just discharge tube. Now, what we had on the previous slide was just, we had this. Where's my pen? Where's my pen? There we go. Okay, we had this part right here that I'm boxing in green. Okay, let me clear it up for you. Right here, the part that's in green is just this part. Okay? There are other lines in the infrared and the ultraviolet that we cannot see with the naked eye. You can detect them. Okay, there are ways of detecting them, but we can't see them with the naked eye. But he came up with an equation, the Rydberg equation, which explains or solves for all of these specific wavelengths for the hydrogen atom. You notice this title of the slide, it says spectral lines of atomic hydrogen. Here's the equation. This is an equation that I'm going to give you on your midterm, this baby right here, okay? I'm going to give you the R. You don't have to memorize that, okay? And he said that 1 over each one of these wavelengths is equal to this constant, 1.09 spinach times 10 to the 7th reciprocal meters, okay? Multiplied by 1 over n low squared minus 1 over n high squared. And you're like, what's n? Well, for the visible series, now here it says n1 is 2 and n2 is equal to 3, 4, and 5. So I'm not a big fan of the low and high. Sometimes I use it, sometimes I don't. But the n1 is the same thing as n low, and the n2 is the same thing as n high, like that. Okay? So what he's saying is this. The visible lines, there's 1, 2, 3, 4 of them that you can see with the naked eye. Okay? For each one of those, if you solve using n low, you have to substitute in the number 2. So if you put the number 2 in there, and if you put n2 is equal to 3, 4, 5, and 6, you will solve, and you solve for lambda, the wavelength, you'll end up with these wavelengths, those 4 wavelengths, okay, which were shown back here. They were 410, 434, 486, 656. Pretty cool, huh? Okay, now we don't go into how he came up with that in detail, okay? And the reason why is I even have this written in my notes that I'm looking at in front of me. It says, Rydberg's equation predicts wavelengths, but does not explain them, okay? And in her book, she even says something really interesting. She said, this is a classic example of a scientist kind of going backwards and just coming up with an equation that fit the data, right? He's actually massaging the equation to make something that fit the data, but damn it, it worked, okay? And you got to admire the guy for coming up with something, you know, that eloquent that worked. All right, give me 1 second. I'll let you read this slide in the meantime about Niels Bohr.
I'm not sure if I'm jumping the gun or whatever, but how do we determine what N1 and N2 are?
How do you determine?
Yeah.
N1, N2, and all those have to be whole numbers, okay? They're always going to be integers. And all I'm telling you right now is that when it's a visible line in the hydrogen spectrum, the N low is going to be 2, okay? But for now, all you need to know is that N will always be an integer, okay?
Okay, thank you.
Yeah, nothing more than that, all right? There we go. So now we're going to switch gears a little bit more. Now, I bet you if you've ever, you know, opened up, if you've ever seen a science fiction movie, so don't write this down, okay? Don't copy down what I'm going to put here. But if you've ever seen The Simpsons or a science fiction show, you might have seen, you know, a structure of the atom where they have all these particles in a nucleus, and then they'll show kind of these funny, this is really crappy drawing, but they'll draw something like that, and they're like, there's your atom, people. You got your nucleus here, and you got electrons buzzing around. Okay, that is not scientifically accurate, so we're going to delete that. We're going to pretend that didn't happen, okay? But Bohr came up with an atomic model and postulated the following. He says the hydrogen atom only has certain energy levels, and Bohr called those stationary states, okay? Each state is associated with a fixed circular orbit of the electron around the nucleus. Okay, good. The higher the energy level, the farther the orbit is from the nucleus. Well, that makes sense. And when the hydrogen is in its first orbit, the atom is in its lowest energy state called the ground state. Now, what I want you to understand is that we're on a journey right now, right? We're on a journey to understand the structure of the atom, modern atomic theory. We're not at modern atomic theory, okay? You can even see here that Niels Bohr, if I skip ahead to the next slide, you know, he died a long time ago. Okay, this is Niels Bohr when he's older, but he died in 1963. Okay, so this is a long time ago. Niels Bohr developed this model. And if you think about it, what he's saying here is he says, okay, you've got a nucleus and you've got stationary states around that nucleus. So you know what? Why don't I just draw the nucleus like this, a single dot like that, okay? And he says, you've got stationary states going around that nucleus, okay? You got ones like this. Forgive me, you guys, I'm not a very good artist. And you're like, couldn't you have picked this as a Google image or something, Mr. D? No. Okay, okay. Anyhow, bear with me. What he's saying is, you got certain energy levels, okay? So here's my nucleus. Nucleus, okay? And he says, you get fixed energy levels around it. He said, the first level, I'm going to call that n is equal to 1, okay? That is called the ground state. It's the lowest energy state. After that, I have n is equal to 2. After that, I have n is equal to 3. After that, I have n is equal to 4. And I can literally go all the way up to n is equal to infinity. Now you're like, well, why would you be drawing a line if it's infinity? I don't know. But anyhow, you can technically go all the way up to n is equal to infinity. You're like, wow, that's nuts. Okay. Well, again, this is a model. Okay. I didn't say the atom looked like this. In fact, it's not exactly what it looks like. But we're on a journey to understand the atom and to get to modern atomic theory. Okay. So give me a thumbs up if you're just with me. Then nothing more than what's on this slide. You got fixed circular orbit, just like planets orbit the sun. The farther they get away from the nucleus, the higher energy level. And when you're at the lowest energy level, that's called n equals 1, and we call that the ground state. So whenever I say ground state, okay, I'll just write it in here. The ground state will always mean n is equal to 1. Okay? I don't want you to ever get confused if I say ground state in a question or a slide or something. So you can see that this made Bohr famous, right? Now it says here, the atom does not radiate energy while it's in one of its stationary states. And the book goes into a little bit of detail about this. I'm not going to go into it right now, but a student asked me a question about this last class. She or he said, you know, why doesn't the electron just cave into the nucleus? Well, the book talks about that a little bit. It says here, the atom changes to another stationary state by absorbing or emitting a photon. So if I draw my nucleus, I'm probably going too slow today, but I just wanted to savor the moment here. So I'm not drawing the whole orbit because, as you can tell, it kind of looks like a Wi-Fi signal, doesn't it? Mr. Dio is not that good at drawing. So n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, n is equal to 5. I can go up to as many n's as I want. But what it's saying here is that the atom changes to another stationary state by absorbing or emitting a photon. So when the electron, when it absorbs energy, right, it's going to go to a higher energy level. So you hit with a certain frequency of electromagnetic radiation, and that's going to absorb energy, right? It's going to be a positive change in energy, right? It's going to take in energy. If it emits a photon, right, it's going to go from a higher energy level to a lower energy level. And then it's going to emit light. So energy is going to be negative because it's going to be given off. And if you're not with me 100%, don't worry. We'll look at examples of this. It says the energy of the photon equals the difference in energy between the difference between the energies of the two energy states. When the electron is in any orbit higher than n is equal to 1, that's an excited state. So again, when n is greater than 1, that's an excited state. So you need to know what a ground state is. N is equal to 1. Anything above that, so n is equal to 2, 3, 4, 5, 6, 7, 8, 9, all the way up to infinity. Those are excited states. All right, well, let's keep moving on. Okay, this is always a fun slide to talk about with my students because there's some heresy on this slide. Yes, I said it, heresy. Okay, there's something that Mr. Dion really doesn't like about this slide that he thinks kind of, and I'll tell you what it is, okay? So look, you have an electron in the lowest energy state. Where's my pencil? Okay, n is equal to 1. It absorbs energy. Whee! Okay, it absorbs energy, and it's up here. And then that wee I just said there shouldn't be doing that. Okay, so I'm going to back off on that because quantum mechanics tells us that this line, and here's the heresy, this does not exist. That red line, that doesn't exist. This doesn't exist. This doesn't exist. None of these red lines exist because what the electron is doing is it is going from, now pay attention closely here, it's going from here to here. Okay, and it didn't follow that path. It just showed up there. You're like, oh, come on, Mr. Dion, that can't happen. Oh, yes, it can. Okay, it's not classical mechanics. Where are you? Where are my students? Okay, go to application. Is anybody out there? All right, somebody says subatomic particles. Woo, okay, good. Okay, so here's classical mechanics, right? My Apple Pencil is going from here, n is equal to 1, to n is equal to 2. I don't know, maybe I could go like this. N is equal to 1 to n is equal to 2 like that. That's classical mechanics. That's what you're used to in everyday life. Quantum mechanics is at the microscopic level. I don't live at the microscopic level, and neither do you. Okay, we're going to do an experiment here as a group. You ready? Here's n is equal to 1. I want you to close your eyes. Open them. Hey, now it's n is equal to 2. Did you see it in between the two energy states? No, because it wasn't there. Okay, watch. We'll do the experiment again. Okay, so we start at n is equal to 1. Close your eyes. Open them. Hey, it's at a new energy level, right? It doesn't pass in between the two. I know it's not intuitive. I understand that, but you got to trust me, okay? That's the way quantum mechanics works. So it's going to take a specific amount of energy to get it to go from n is equal to 1 to n is equal to 2. All right. Anyhow, that's my best explanation I can do right now. Does that help at all? I hope it helps somebody. Hey, it helps 3 people. I'll take it. Good. Thank you, Matthew, Joel, Brianna. Great. Excellent. Good. Now, where the heck was I? Where are my slides? I know it's not intuitive, you guys. I know it's not intuitive, but I need you to understand that that's the way it works, all right? I don't want you to come out of Mr. Dion's class and be like, well, Mr. Dion never told me what quanta means, you know, what quantized means, okay? Anyhow, again, before I end on this slide, absorption is when it's taking in energy. Energy is going to be positive. Emission is going to be negative, right, because energy is given off. All right, so let's keep moving, and we'll talk about the same subject even more. So somebody just unmuted their mic and said, I can't remember exactly what the question was, but it says, like, how do I know what N is? Well, N, again, is the ground state. So this is probably a better picture than I could ever draw. You have the nucleus. Here, you can even see the positive charge in the nucleus. You have N is equal to 1, 2, 3. Sorry, I'm not labeling them properly, am I? N is equal to 1 is this one here. N is equal to 2, 3, 4, 5, 6, right? Anyhow, so what we can see, so what the heck was happening in that hydrogen gas tube with the pinky color? What is happening is you're taking the hydrogen atom and you're putting energy into it, right? From the electric current. There are a lot of hydrogen atoms in there. So you got lots of electrons absorbing energy and lots of electrons releasing energy. Why would they be absorbing energy? That comes from the current, right? And that's going to move them from a lower energy state to a higher energy state. And if you're like, well, which one? I don't know. It could be anyone, right? It could be from n is equal to 1 to 5. It could be from 1 to 4. It could be from 2 to 5. It could be anything. All these different transitions are happening in time. We're talking about moles of atoms here, people. We're talking about a huge sample. So in order for an emission spectra, right? Emission is the spectrum that you can see with the eye. What's happening is the electrons are going from a higher energy level. For example, the violet line, right? This is violet here, is occurring when the electron is going from n is equal to 5, sorry, n is equal to 6, sorry, I can hardly see. So n is equal to 6, this is n is equal to 6, down to n is equal to 2. So if you plug those numbers, now I really got to back up here. You plug those numbers into here, and you're going to end up with the violet line. Okay? Does that make some sense? I hope it does. Okay? The other lines that you can see are shown right here, right? I told you there was a violet line. I told you there was an indigo line. I told you there was a blue line. And I told you there was a red line. Now, you don't have to have these memorized. No, I just want you to understand what the heck is going on. And if you're like, well, Mr. Dion, if an electron absorbed enough energy and it went up to a higher energy level, couldn't it give an emission going down to n is equal to 1 that's even more stable? Yes, it can. But the thing is those wavelengths that are given off are ultraviolet wavelengths. You cannot see that with your eyeball. I'm pointing to my eyeball right now. Hey, Mr. Dion, couldn't it go down to n is equal to 3? Couldn't that happen? Yes, that can happen too. But those are also wavelengths that you can't see with the naked eye. Hey, Mr. Dion, couldn't it go to n is equal to 4? It's not even on here. Couldn't that happen? Yes, that can also happen. Also, it's going to be something that you can't see. Okay? Again, I keep asking for confirmation, but this is not a simple concept. I want to make sure my students give me a thumbs up if you follow me. Even 60% of the way is good enough for now. Good, because you will have to read this. Okay? I recommend reading this, even if you have to go to another textbook to get clarification. Maybe if you need to do that. Now, Bohr's work led to an equation for the energy levels of the hydrogen atom. Notice that I'm very careful about what I'm saying on these slides. Right? I'm very careful that I say that it is it is for the hydrogen atom. Notice I'm not saying it's for any other atom. Okay? He came up with this equation, and then to find the energy difference between two levels, he developed this equation. So delta E delta E is equal to negative 2.18 times 10 to the minus 18 joules multiplied by 1 over n final minus 1 over n initial. Now, you might be looking at this equation and be like, hold on a second. This looks an awful lot like Rydberg's equation, right? You're like, this looks almost identical to Rydberg's equation that you showed me way back here. Okay, it looks very similar to it. I have a constant, I have n low, n high, same concept, okay? N final, n initial, whatever. Now, what I would say to you is this, the way I describe it is like this. I say, this is Rydberg's equation. Where's my Bohr's equation, okay? This is Bohr's equation. I say it like this. To me, it's like it's two flavors of the same equation. And if you're like, why would I need two flavors? Well, it depends on the situation. If you're looking to find the difference in energy levels or difference in energy between two levels, I would use this equation. If you want to find the wavelength of light that's emitted or absorbed between two energy levels, I would use the other equation. Okay? And if you're like, well, can I derive them from each other? Will you give me the constants? Of course, I'll give you the constants. Okay? This class isn't about, I make you memorize some things in this class. I freely admit that. But if it's a constant, I'll give you that. Okay? The only constant I think there's probably a few. You guys are going to catch me in my speech here, but some things I don't give, like maybe ideal gas constant. But anyhow, we got 5 minutes. Let's try a problem, and then we can probably call it a day. After that, and then next week, what's today? Wednesday? Yeah, next class we can even get into the rest of this chapter. Let's finish this one quickly. It says here, a hydrogen atom absorbs a photon of ultraviolet light. Look at the figure. And its electron enters the N is equal to 4 energy level. Okay? Calculate A, the change in energy of the atom, and B, the wavelength of energy. And you're like, darn it, now we need both equations, okay? Well, anyhow, let's just start with energy first. So we'll start with Bohr's equation because they're asking us for that first. I'll rewrite the equation for you here. It's delta E is equal to negative 2.18 times 10 to the minus 18 joules multiplied by 1 over n final squared minus 1 over n initial squared. Now, they've given us the n is equal to final because it's absorbing, right? So if it's absorbing, right, it's going from low to high, right? So that tells us that n final is going to be equal to 4, right? Now, I'm just going to throw this out there. I know it's late in the lecture. Does anybody know what n initial is? Did anybody able to pick that up based off of what ooh, I got a couple of KG students out there who are way ahead of me. Yeah. So it says here that it's UV light. Okay. I'm going to back up here. Maybe I'm taking too long, but when it's ultraviolet light, let me back up. Okay. If it's ultraviolet in its absorption, okay, it's going from n is equal to 1. Right, n is equal to 1, and they're saying you're going from n is equal to 1 to n is equal to 4. Remember, all these lines are pointing in this direction. That's emission. We're talking about absorption, right? We're talking about going in the opposite direction. So with that in mind, let's plug these numbers in. So I'm going to go over here. Let me just copy this. It might take too long. Whatever. It's landing free. Copy. Let's finish this thought, you guys. Okay, so there's my equation. We'll just solve the first half of the equation, or the first half of the problem. So I'm going to have delta E is equal to minus 2.18 times 10 to the minus 18 joules. My n final and my absorption is n is equal to 4 squared minus, so n final is equal to 4, n initial is equal to 1. Again, this is absorption, so I'm going from a low number to a high number. 1 over 1 squared, that's pretty easy to solve. Anyhow, I've gone ahead and done the math already here, so that works out to be negative 2.18 times 10 to the negative 18 joules multiplied by negative 0.9375, like that, and you get that delta E is equal to 2.04 times 10 to the negative 18 joules. Now keep in mind that you ended up with a negative number in here, and you take a negative times a negative, and you end up with a positive number. The delta E must be positive because this is absorption. Okay, absorption. If you're going from a low energy level to a high energy level, you got to take in some energy, right? Okay, we could solve part B. It's 10:39. We got one second left. You want to wait and solve this the next class. Anyhow, for this one, you just use E is equal to HC over lambda. You rearrange this to lambda is equal to HC over E. You have E, this is a constant, this is a constant, and you end up with a wavelength of, I got 97.4 nanometers, which of course you can't see, right? All right, let me just stop presenting here and talk to my students for a brief second. Cha-cha-cha-cha-cha. Who enjoyed this lecture? I think this is kind of a fun one. Learn something really different. Really get into the structure of the atom. I find it's really interesting. In fact, a lot of what we do in this chapter deals with quantum numbers, which is kind of more, which is things we're going to learn next class. But I find that this lecture is actually, I find it more fun. I shouldn't say that. I shouldn't be partial towards anything, should I? But I enjoy this lecture. I enjoy just talking about emission and absorption. I think maybe because it's one of the first things I ever taught in chemistry, in the first class I ever taught in Canada. So maybe it's just something I've always enjoyed. Anyhow, so if you could do me a favor, I know that most of you have already finished the Learn Smart, but if you could just, take a look at the rest of the chapter and try to read it before Friday's class, that will make the class a lot more interesting. And I'll tell you why. I know that class is over, but you can stick around. I'll give you another heads up, is that it will make the part about quantum numbers, it will make it a lot funner for you on Friday. It will just make it that much more enjoyable, because I've seen quantum numbers is not something that's mind-boggling or anything, but I find that students get mixed up. They get mixed up. They're like, which one is which? What's angular momentum? Which one's principal quantum number? Which one's spin, right? They'll get mixed up sometimes. So if you look at it ahead of time, you probably won't get nearly as mixed up, if you will get mixed up at all, okay? So that's my recommendation, is to really take a look at what quantum numbers are before coming to class, because I will guarantee you I will ask you questions about those on the next midterm. In every ACS final I've ever looked at in my life, they always have questions about quantum numbers, okay? Anyhow, so on Friday, we'll try to finish up chapter 7. I always like to do some practice problems along the way. Looking forward to it. And, well, have a good rest of your day. I'll post this recording to my YouTube channel, same as always. See you later.